So I had a request from somebody asking what we could do to talk a little bit more about the code. I've told you I've been hesitant to really jump in and dig deep in the code because I do feel like there is a definitive need for me to really make you do this. I know I hate to be blunt like that, but part of coding and part of getting better at coding is just struggling through the code. If I sit down and I give you the code, you're not really getting better at coding. This is a frustration, and this is something that you need to dump a lot of time into. So I anticipate that. Now, with that said, what we're going to be dealing with for this code is we're going to be handling a lot with our inputs and our outputs. Okay? Ultimately, you can look at this box as if here's your code, you have a number of inputs, and you have a number of outputs. Okay? The outputs from your code, you have 4 of them. Okay? You have one of them goes to an N-type MOSFET, one of them goes to another N-type MOSFET, one of them goes to another N-type MOSFET, and one of them goes to your P-type MOSFET. Okay? You have 4 outputs from your code. Now you also have 4 inputs to your code. Okay? Those 4 inputs to your code are your photoresistors and your 2 switches. Okay, now the way that I've set up this hardware for this project is that one of your switches is involved in color control, and the other one is involved in light intensity. You pick which one. It doesn't matter to me which one does which. Your 2 photoresistors together work together for that. So when it comes to setting up your ADC is what's going to handle all 4 of these inputs. All of your inputs to your Pi come from your ADC, whereas all of your outputs come from your GPIO.outs. So we'll cover a little bit of that right now. Let's start with this idea of your ADC inputs. Okay? Now, what I'm going to do is I'm going to go ahead and I am going to switch to my desktop. So let me do it quickly. I'm going to use my phone so that it's a little cleaner of a transition. So what we have here is this is a basic ADC code. It imports the Adafruit where is it? ADS 1X15 situation. Now this specifically targets the 1115. So that's why I'm using this. This information, by the way, is available on GitHub. It's the GitHub for the Adafruit Python ADS 1X15 value. And there's information on how to download this library and use it. So I would, at this point, if you haven't already downloaded your ADS library, I would just go ahead and use the GitHub because it has nicer documentation. Now this one, the file that I'm looking at is one of the sample files, and it's called the simple test. And what this does is it goes and it reaches ADC. So first of all, it starts out with ADC is equal to Adafruit ADS 1X15. dot ADS1115, and then parentheses. Okay, so it starts off with this. That's how you call the ADC. It goes ahead and it sets the gain at 1, which is fine. Gain allows you to change what the scale of the values are. I would rather not play with that at this point. And then what this does is, if you were to just copy and paste this code in, first of all, it's a great way to check and see whether or not the ADS is working is to use the sample code that is given to you with the library. If the sample code doesn't work, there's a problem. That's not so good. So what this does for its readings is it says for I in range 4, and it goes through and it reads each of the 4 channels and it portrays it, okay? We do have these 4 inputs, so it'll start at 0, 1, 2, 3. And that's how it figures out what each of those values are. Now, once the ADC value has been collected, so let's say I'm just going to say let's say I'm going to call photo 1. Photo 1 is equal to ADC dot read ADC parentheses, and I'm going to go ahead and say, all right, it's in range 4, so we'll go ahead and read first one, and we'll say gain equals gain. Okay, that says gain equals gain. Okay, so I'm just copying down the code here. I'll go ahead and switch back to my camera view so you can see me write this out. Okay, what this will do, if I were to type this code in, is the output of this is I will get photo 1 is equal to some integer number between 0 and 2 to the 16th. Which, by the way, 2 to the 16th is, I don't know, I actually think I've calculated that in this class. It'll give you some number between 0 and 65,536. Okay? Where if it's closer to 65,536, then it's on the top end of what it's reading. Basically, this represents reading in 5 volts, 0 represents reading in 0 volts, and you have a linear scale in between. So, well, that's kind of annoying. But reading these values in here, you get some integer number. So let's say I read 40,237. Okay, what do I do with that? Now that I have a photoresistor ADC value of 40,237, how do I process that to get something useful out of it? From the last video, we talked about how we need to then convert that into a number that can be directly used for whatever that is. Whether that be PWM control or whether that be color control. So let's say we're going to specifically look at the color control aspect of this code. Okay, so we get this value in, it comes in at, for example, I just wrote 40,237 as an example. We get that number. All right, now when I go to actually do my code, I have this value in, and let's say I have, okay, let's say photo 2. I do the same thing except for I have photo 2 is equal to this, and then instead of 0 it's a 1. 0, 1, 2, 3. Okay, so I got this is 30,222, and switch 1 is equal to 10,489, and switch 2 is equal to 56,778. Okay, So those are my 4 numbers. Now I'm going to bring those in. This doesn't actually do anything. I can't directly output this. This is a raw data value that has to be processed before it means anything. Okay? The system itself doesn't really know what 56,778 means. So you have to put it into the spectrum of 0 to 65,536. In order to do that, what we're going to do is we're going to say switch 1. Let's say this is for color, and we'll say switch 2. This is for PWM control. Okay? Just, again, I'm picking things. I don't know how this is arranged on your ADC. I don't know how your connections are arranged. So I'm not really sure which one of these is going to go to what on yours. I'm just making up an example. So let's say switch 1 is color. Okay? So what I'm going to do with my color switch now is, as we talked about last time, we need to establish 7 unique bins related to colors, or you could do 4 unique bins if you just want to have red, green, blue, and white, or 3 unique bins if you only want to do red, green, blue. But I'm going to go ahead and say this is blue. We'll go next color is purple. We're going to go next color is red. And then we'll go orange, green, and yellow, and then white. So those are my 7 bins. Okay. Now, my 7 bins for my switch, if I draw my switch, it's wherever my switch is located. I want it to be, if it's inside this bin, it's blue. If it's over here, and the center line of the thing is inside of this bin, it's purple, etc., etc. Okay. Now you can do as many bins as you want. You don't have to do all 7 colors. It's not a requirement for this. It's just what I've done. So for here, what we're going to end up doing is we're going to have to establish color boundaries. Okay, how do we know this is within a certain spectrum when you're reading a number between 0 and 65,536? In reality, the ADC is going to produce a value of 0, and then over here on the far end of the white, this is 65,536. Everything in between is a different color. So if you look at switch 1 being 10,487, well, that's actually really close to right here. So my switch would be in the purple range there. We're reading 10,000. Okay, so how do I tell my system that I want it to be purple? There's a number of ways to do it. I'm going to show you one way. You do another way, great. Okay, what I'm going to start by doing is I'm going to force this into 7 unique bins. And by doing so, what I'm going to create is a spectrum. So I'm going to go ahead and I'm going to take switch 1 and I'm going to multiply it by 7 divided by 65,536. Now, why am I doing this? When we divide by 65,536, then what we're doing is we're creating a percentage that now switch 1, well, let's say we're calling this color, okay? Where now color is a value that is a percent of the total thing. Where now the left side of the switch is 0% and the right side of the switch is 100%. Just by dividing by 2 to the 16th, we turn this into a spectrum. So that's pretty awesome. Now I multiply this by 7 so that this value now goes from 0 to 7. Instead of 0 to 1, it now goes from 0 to 7. Now what am I going to do with that? Well, I have each of my distinguishing markers. From 0 to 1, that's blue. 1 to 2 is purple. 2 to 3 is red. 3 to 4 is orange. 4 to 5 is green. 5 to 6 is yellow. And 6 to 7 is white. That's how I did it. So just by implementing this code, I've now broken this down such that inside of that individual integer, I have a color range. Okay. Now there are ways of doing this that are great. But what I would say is now to take this value, this is all the processing we need for the color. We've taken this and we've turned it into a useful value that identifies which which range it is in. If we switch the switch 1 to a different value, we'll read a different value, and it'll identify what bin it is in just by doing this simple math formula. Now we're going to take this and we're going to convert it into output, okay? And the output is going to affect these three, because those three impact our colors. Let's say this is the N type for red, this is the N type for green, and this is the N type for blue. Okay, you have all three of those connected to N-type MOSFETs on your system, so that's where we're at. Okay, what I'm going to go ahead and do is I'm going to say, all right, I'm going to create an if-then spectrum. So if color is less than 1. If it's less than 1, it falls in what I've identified as the blue spectrum. Okay, if I have a blue spectrum, then what I want to do is I want to turn off green and red and turn on blue, because that's the only way to get a blue light. So if, then what we have is GPIO dot output, and then you do, let's say we named all of our pins after our colors. Red will be 0. GPIO dot output green will be 0, and GPIO dot output blue will be 1. So this will turn on blue, turn off green, turn off red. Great. So if the color is less than 1, meaning it's falling into the spectrum, now we do this. Okay? But if it doesn't, then we create an elif statement. Else if color is less than 2. Okay, now if it's less than 2, then it's in the purple spectrum. Now if it's less than 1, then it won't ever run this potentially into the purple spectrum. But all we need now is if it's less than 2, it'll fall in this purple spectrum. And then we can say the exact same things here. We want red and blue. So here in this case, we'll do all three outputs. We got a red will be 1, green will be 0, and blue will be 1. I'm not gonna go ahead and write that out because I'm running out of space. Okay, this is how we do it. And then we have a total of 7 of these codes indicating colors and how those colors correlate. So this is how you do the input, processing, and output for your color spectrum. Okay, and I'm not going to go ahead and write out all of them, but that's how I would do it. There are multiple ways of handling that. As long as you take one, we'll be fine. So there's the color spectrum. Now for the PWM cycle, which goes on the PWM pin, which is connected to your P-type MOSFET, we're going to be using switch 2. Now the idea behind a PWM is a PWM issues a range of values where the net mean of all of those values is equal to some percentage of the maximum. And that percentage is this value divided by this value. So it's the percentage of how much is on divided by how much it's off. This is called the duty cycle. Okay, at 100% duty cycle, what you have is you have maximum power. Okay? For a switch like this, what you want is for 100% of your duty cycle, your PWM pin, which is coming from your switch, is going to be reading the maximum number. It's going to be reading 65,536. So at 65,536, you want 100%. At 0, you want 0%. Okay? So you have that range, and what you're doing is you're actually setting up, okay, I want to create this value based on what I'm reading as a percentage of my ADC. Now we created percentages in the last time. Simply by dividing switch 2 by 65,536, you then create a percentage from 0 to 100% that indicates how strong, how close to completely on switch 2 is. Okay, and if you wired your system backward, what you will find is that at 0%, well, at one side of your switch it reads 0, at the other side it reads 100. If you wired your switch backward, it just means left side will be 100, right side will be 0. You can make a quick adjustment for that if you want to say, oh no, I want my switch to be so that 100% is on the right side, not on the left side. Then what you can do is so to get it as a percentage, switch 2, I'm going to call this intensity, is equal to switch 2 divided by 65,536. Now this produces a percentage value, okay? And then this percentage value, if I have it switched so that my switch is left is 100% and right is 0%, I can change that by having just a very simple intensity is equal to 1 minus intensity. And it inverts it, flips it over, and it means so that now on the right side you have 100% and on the left side you have 0%. Okay? So you can do that, that is perfectly fine. That is 100% acceptable. Okay? But only do this if you need to switch your colors. You can also do this for your number. For your color spectrum, you could, instead of having 1, it'd be 7 minus color. But you can do that where it flips inside of the code which side is positive and which side is negative. So all code corrections. Now for actually addressing the PWM pin, what you have to do is, let me look this up real quick. So I'm going to quickly change this to my desktop background again, so that you can see what I'm doing. And I'm just going to go here and look up GPIO PWM output Raspberry Pi. Okay, and what this will give you is a list of people who like using the PWM output on the Raspberry Pi. There's tons of information here. So to set up Up Wpcm, you have to do that no matter what. Then you set up your pin number. Here we're going to be using 12 as an output. You can just simply turn it on. But in order to get this, what you have to do is you have to set your PWM and then start value, and then here, this value inside of here represents 50%. Okay, so you would have to take your intensity value that I wrote up on the board, multiply it by 100, and plug it into PWM start, and have that be this. You can also change duty cycle. So the first time you do it, you would probably start at 0%, and then every time you do an update, you're going to use change duty cycle. Okay, and that's pretty simple. So I'm going to go ahead and switch back to the board now that we've looked at this. And so in your code, in order to set up your PWM pin, we're going to do, we'll set up GPIO dot setup, and then we'll do pin 12, which let's say pin 12 is what we called PWM, and this will be set up as an output pin. Okay, so that'll go way up in the top of your code. Then the next step is, what I would do right under that is I would say PWM is equal to GPIO.PWM, and then, oops, sorry, this is not lowercase, it's uppercase, PWM, and we'll say that's the PWM pin, and then we have to establish a frequency. Okay, for this frequency, I'm going to go ahead and go with 1,000 just because that's what's pretty common. And then right underneath that, PWM dot start, and then I would start at 0. Okay, so it turns on the pin, but it turns it at a 0% duty cycle, so it just isn't turning on at all. Okay, you put this up at the top of your code. Now, inside of your while loop, while you're reading these values and adjusting them, what you're going to have to do is take this intensity value and output it. Once you've calculated your intensity value, as I said earlier, you're going to have to multiply this by 100, or really you're going to have to multiply this by 100, because the PWM change duty cycle has to be a number between 0 and 100. And you may have to convert this into an integer, depending on how your pi is. I'm not actually sure if that's the case. If you do have to convert it into an integer, then you do intensity equals int intensity. Okay, and then it just converts it into an integer. So you can do that if you have to, if you need a number between 0 and 100. Okay, so now that you have that, you've already got the PWM started up the top of the code. And what we'll do is we will say PWM dot change duty cycle, and then we'll put in intensity right here. Okay, and that's it. This is the output. It sets the PWM duty cycle to whatever the intensity is of switch number 2. Okay, I hope that's informative. I will say that I have been thinking about integrating the photosensors. For right now, there's nobody who's really close on getting this done. So for right now, what I would suggest is, let me check and see. Okay. What I would go ahead and suggest is ignore your photoresistors in your code. Read them in because you know how to, but you don't need to have them do something. Ideally, we would take these values and use them to create a closed loop feedback system. But I'm just going to have you talk about that in your paper, and I'll discuss this a little bit more in the next lecture. I just don't think we have enough time. Unless I'm going to sit down and tell you how to do it, I don't think we're going to have enough time to implement the feedback into this type of system. So, sadness. All right, I will post another lecture on Thursday. I do want to talk about block diagrams because that is part of your paper that you have to write. Other than that, I don't have anything else for you. So, yeah. Next week we're going to do a review over materials for this class, and that'll be it. We're done in 2 weeks.